So, what's the real difference between an AI that's truly intelligent and one that's just, faking it? We see AI do all these incredible things, but the real test isn't getting them to work in a controlled lab. Nope, it's making them reliable out in the messy, unpredictable real world. Let's dig into how we build an AI that genuinely learns.
Think about it like this, right? You've got a student who's prepping for a huge exam. One of them actually gets the material, like deep down. They can tackle new problems they've never seen before. The other student, they've just memorized the answers to the practice test. Now, both of them might totally ace the practice questions, but who's really going to pass the final exam? It's the same exact challenge in AI. We're trying to build a genius, not a cheater.
And that brings us to what is maybe the single most important goal in all of machine learning: generalization. This has nothing to do with memorization. It's all about a model's ability to take what it learned from its study material, the training data, and apply that knowledge correctly to new stuff it's never seen. I mean, you need a spam filter to catch tomorrow's spam emails, not just the ones you showed it yesterday. That right there is generalization. Now, the big, bad enemy of generalization is this thing called overfitting. This is our student who just memorized the answers. The model becomes so obsessed with the training data that it learns everything, not just the important patterns, but all the random noise and weird, irrelevant quirks too. It fits those practice questions perfectly, but the moment you show it something new, it fails. And usually, it fails spectacularly. And this quote from the team at Apex Machine Learning just hits the nail on the head. If you test your model on the same data you trained it on, you're not measuring learning, you're measuring memorization. That's so important because it gives you this completely false sense of confidence. You think you've got this brilliant A-plus student, when what you really have is a model that can't think for itself. So how do we give our AI a fair final exam? We know we can't trust its performance on the practice questions. Well, the solution is actually pretty simple, but it is incredibly powerful. We split our data up into separate buckets, and each bucket has a very, very specific job. Okay, here's the breakdown. We create 3 separate data sets. First up is the training set. This is the biggest piece. It's the textbook and homework the model studies from. Second, we have the validation set. Think of this as a bunch of mock exams. We use it to tweak the model to find the best study strategies, all without ever looking at the final exam questions. And then finally, we have the test set. This is the real deal. It is kept under lock and key and used only one time to give our model its final, completely honest grade. And what I love about this is how it really spells out the different roles. The training set is for learning. That's your practice questions. The validation set is for tuning. That's your mock exam to see which study habits work best. And the test set, that's the final. Now, here's the key. You can take the mock exam over and over again, but you get one and only one shot at the final. That discipline is what keeps the model from just learning the test. But building a good model isn't just about splitting your data right. It's about finding this really delicate balance. See, the model can't be too simple, or it's going to miss important patterns. But it can't be too complex either, or it'll just memorize every little thing. This whole puzzle is known as the bias-variance trade-off. All right, let's break these 2 charts down, because they tell a really important story. Over on the left, we see that as we throw more training data at the model, the test error goes down. That makes sense, right? More examples help it generalize better. But the chart on the right is where things get really interesting. As we make the model more complex, giving our student more raw brain power, the training error just keeps going down. Of course it does. It's just getting better and better at memorizing. But look at the test error. It goes down, hits a perfect little sweet spot, and then it starts to go back up. That's overfitting, right there in action. The model's so busy memorizing details, it's forgotten how to think. And that U-shaped curve is the perfect picture of our goal. Way over on the left, you've got underfitting. The model's too simple, it's missing the point. Way over on the right, you've got overfitting. The model's too complex, it's just memorizing noise. Our entire job is to hunt for that perfect sweet spot right at the bottom of the curve, where the model is just right. This bullseye gives us another way to think about it. The little red star in the middle, that's the truth, the perfect answer. A high bias model is like a student who totally misunderstands a key concept. All their answers are clumped together, but they're consistently wrong. A high variance model, that's a student who panics on the test. Their answers are just all over the place. What we want is a model with low bias and low variance, one that is both accurate and consistent. Okay, so besides just trying to find the perfect model size, how can we actively teach our AI better study habits to stop it from overfitting? Well, data scientists have a whole toolbox of tricks for this. The first one is one of the simplest, but also one of the most effective. It's called early stopping. It's basically like telling our student, okay, you've studied enough. If you keep cramming, you're just going to start overthinking it and memorizing useless details. We just watch the model's performance on the validation set, our mock exam, and the second that score stops getting better and starts getting worse, we just pull the plug. We stop training. This graph shows it perfectly. See the training error in blue? It just keeps on dropping because the model never stops getting better at memorizing its homework. But look at the validation error in red. It hits a minimum point, and then it starts to creep back up. That vertical dashed line, that's our golden moment. That's the exact point to stop right before the model's knowledge gets too specialized and brittle. Another really powerful technique is called weight decay. You can think of this as forcing the model to find the simplest possible explanation that fits the data. It works by adding a tiny little penalty anytime a parameter in the model gets too large. This basically discourages the model from putting way too much importance on any single detail and forces it to find broader, more general patterns instead. And then we've got ensembles. I mean, why rely on just one expert when you can ask a whole committee? The idea here is just to train several different models and then average out their predictions. What happens is this cancels out all the weird individual mistakes each single model might make, and that leads to a much more stable and accurate final answer. It's a classic case of the wisdom of the crowd. All right, now, even with all these smart techniques, there are still ways a model can accidentally cheat. To get a truly honest look at how well it's doing, we have to be super careful about one major pitfall. And that pitfall is called data leakage. This is what happens when your model accidentally gets a sneak peek at the test answers while it's still studying. It's a subtle but absolutely catastrophic error that makes you think your model is a genius when really it just had access to information it would never, ever have in the real world. So how does this even happen? Well, one of the most common ways is when you apply some kind of data preparation, like scaling your numbers to the entire data set before you split it. You've just let your training data learn something about the test data. Another classic mistake is including information that you just wouldn't have at the time of prediction. And the absolute cardinal sin, using your pristine held-out test set to tune your model. At that point, it's no longer a test. It's just more training data. But here's the thing. Even if you do everything right, you split your data perfectly, you use smart training techniques, you avoid any and all leakage, there is one final, unavoidable challenge that every single AI model has to face. 91%. That is a huge number. But what does it represent? It represents the percentage of machine learning models that suffer from something called model drift. You see, the world isn't static. Customer behavior changes, new products come out, the economy shifts. All the patterns your model learned so perfectly during training will eventually become outdated. Model drift is the slow, inevitable decay of a model's performance simply because the reality it's operating in has changed. And this really leaves us with the ultimate question, doesn't it? Building an AI that truly learns isn't a one-and-done kind of thing. It's a constant cycle of training and validating and monitoring. Because the hard truth is, making sure a model works perfectly today is only half the battle. The real challenge is making sure it still works tomorrow.